Picking up where we left off with the last lecture, we were really kind of focusing on this equation here for kinetic energy, and we're making the comparison of two different gases. And I'm going to set them equal to each other, that they have the same kinetic energy based on them being at the same temperature, at some given temperature. Okay, so if I set them equal to each other, I'll have 1/2 m1 v1 squared is equal to 1/2 m2 v2 squared. Now, of course, the halves are going to cancel out. And if I kind of put like terms on the same side, I'd have m1, m2, and v2, v1 squared. And I could do this a couple different ways, but I want to get rid of these squares here. So I'm going to take the square root of both sides. Still, m1 over m2 is equal to v2 over v1. And this is Graham's law of diffusion, making the comparison almost like an inverse relationship between the square root. So how these gases compare to each other based on the square root of the molar masses. Okay, let's do a little example problem. An unknown gas. It happens to be diatomic, so pay attention to that. Remember, there's 7 of those, the Hofbrinkels, so just keep track of that. So an unknown diatomic gas effuses. Effuses means it goes across a container at its speed at a rate of 0.355 times the rate of oxygen, which is O2. So that's the information we have about this gas, who it is, how it behaves. We want to calculate the molar mass of an unknown gas and, of course, identify it based on its molar mass. Okay, so how we will treat this particular setup here is I'm going to focus on the velocity of this gas in comparison to oxygen. So calculate the molar mass of this compared to that. And I'm just kind of setting it up here, figuring out what I know, what I don't. This will be the setup. Now, what I know based on what it says, an unknown gas is diatomic, it fuses at a rate of, and here it is, 0.355 of oxygen gas. So that's what I'm going to base this off. So the velocity of this unknown gas is in comparison to oxygen. That's what I know. So I can actually put this in place of x up there. So let's go ahead and do that. So VO2 times 0.355. So this is just good problem solving skills. So it's not just straight up always just chemistry, it's problem solving. Molar mass of O2 and molar mass of X. So given this information, that variable is now gone, which is really kind of nice and important. And I am just left with this number here. And as far as when I put a number in here, that's going to change a little bit because these are velocities, right? So let's take a look at how we're going to do this. I want to get rid of this over here as well. So I'm going to do 2 steps together. I'm going to take this and square this and this to kind of get these guys free of that square root. So in doing so, I still have the 3.55, but now I'm going to be squaring it eventually. And now I can simply just say, based on the molar mass of oxygen, which I know, and the molar mass of X, which of course we don't, but I can get a number out of this. So 0.126 is equal to its oxygen, that's 32 grams per mole, over this unknown. And if I switch these guys around and divide 0.126 into the 32, you will end up with the molar mass of X equal to, drum roll, 254 grams per mole. Now don't forget, it's diatomic. So we have to divide this value by 2, and that gives us 127 grams per mole. And if it's 127 grams per mole, and I look over on the periodic table, I will find that that happens to be, I'm sorry, I had it sitting over here the whole time, and I'm not pulling this up so you can see it. Sorry about that. The answer would be iodine, doing the work there along the way. Okay, of course you can pause this and take a look at it and write that down, or you're just following along. So nice little problem-solving problem to take a look at in comparison for Graham's law of diffusion. I can tell you that College Board probably will not ask you to do a problem like this, but they may ask some relative questions as far as how they behave. So the big takeaway from this kind of a problem is heavier gases move more slowly than lighter gases. Heavier gases move more slowly than lighter gases. But here's the trick question. Which one has more energy? The light gas or the heavy gas? And you may be apt to say, well, either one, I don't know. But the fact they're at the same temperature, one gas is heavy, one gas is light, less massive. They have the same energy, only because they're at the same temperature. So they compensate based on the fact that, pull this up over here, light, less massive gases move more quickly. Heavy, massive gases move more slowly. And you can probably kind of think about that in regards to, like football players. Wide receivers are really fast, but they don't have a lot of mass. Where linemen, they're really heavy, and they typically move more slowly. However you want to think about it. That works for me. Okay, that is the end of the lectures.